Uh, this is example in this textbook. Example number is 3.25. In this problem, we are talking about the series resistor. And when the resistor is connected in series, then what happens in the viewpoint of the voltage? We call that is a voltage division because the Vs is voltage is applied to the series connected resistor. Then the voltage to terminal will be the same with the Vs. But in this resistor, the voltage will be divided. So we call that is a voltage division. Problem is there are two resistors, R1 and R2, and Vs is applied to this terminal R and R2. Then we want to know what is the value of the voltage applied to the R2. So we'll make something like a different way. So my target is design voltage divider. We want to divide this voltage through this R1 and R2. So specify the value of R1 and R2 to satisfy this specification is 1 and 2. So first spec it was input and output voltage related to VO is 0.8 Vs. So to make that, we want to make in this way. So based on, we can calculate the R1 and R2 simply. The circuit looks like that. This is the Vs, and we make a series register and R1 and R2 in this way. We want to design that two register R1 and R2. We have two spec. First spec is V output voltage. V out is 0.8 Vs source voltage. And second spec is source power. Should be less than 1 milliwatt. There is a two specification we should satisfy here. And Vs will Vs is 20 volt. So to get there, based on two specifications, we can design R1 and R2 respectively. First, because this is a V out, so based on that, we can get a relative equation with Vs and Vo. What is that? Because that is a Vs, based on that, R1 voltage drop here, the V1, and this is a V2. So Vs is V1 and V2. And we define this is current I. Then Vs is R1 plus R2 current. Oh, this is I, current. So this R1I and R2I. Then we can define this is a V1 and this is a V2. So when say Vs is R1 plus R2I and V2 is V0 is R2I. From here, current is R1 plus Vs. We connect here. Then V out is R2, R1, R2, Vs. So R1, R2, R2, Vs. Based on this equation, you can say VO is R1, R2, R2 Vs. So we say when voltage are here, then voltage divides that voltage here based on the values. So we call this a voltage divider. So that should be 0.8 Vs. So that means that value should be 0.8. So R1, R2, R2 should be 0.8. Based on there, what is that? 0.8 R1 plus 0.8 R2. So 0.2 R2 is 0.8 R1. So R2 should be 4 R1. There is a first requirement based on this specification 1. So R2 should be 4 R1. Second thing is the power. So what is the power supplied by source? That is a power PS is VSI. Then when say this is 20, then how much is it? 20 is current. I is that value. R1, R2 over 20. That should be 0.001. So based on that, this is here 400 R1, R2. That is that. So R1 plus R2 should be larger than 404. And here R2 should be 4 R1. So based on that, this is R1 plus 4 R1 into 5 R1, which is larger. So R1 should be larger than, that means 80 kilo ohm. So R2 should be 4 R1 is 320 kilo ohm. So if we design R1 is 80 kilo ohm and R2 is 320 kilo ohm, then that is a voltage divider. There's a voltage divided based on that is 0.8 Vs, and the power supplied by source should be smaller than the 1 milliwatt. There is a specification. So that design values satisfy the two specifications. This is another example. Here, this problem, we should consider two similar voltage divider as here, and they use the voltage divider to determine the voltage or voltage V2. And here, so they're just same things, same problems. What's the different? The different thing is the V2 is polarity of V2 is here is plus, and this is minus. The voltage is the same. Resistor is 1, 400, 300, 1, 400, 300 the same, and contradiction is the same. But our voltage direction is V2 is plus here, and VB, this is a plus. So polarity is different. So we can calculate the V2 and VB, but two values are different. That means the direct polarity of voltage is, the definition of polarity of voltage is different. This is deal with about how to define the voltage direction and current direction. So that is, we have choose the every polarity direction and every current flow direction. So that depending on the definition. So we don't need to worry about that. Anyway, we solve that. At first, we will get the V2 here. How to get that? Because we know the voltage divide, the 12 volts and 100, 400, 300, and our question is only voltage drop caused by 400. So Vs will be 100, 400, 300, and 400, and voltage source is 12 volt. Wow, it's very simple because this is 800, 400, 12 is 6 volt. Alright. And another way to get the depth value, I'm sorry, it's long. This is not Vs, this is a V2. Another way is we need to get a first I current is 100, 400, 300, and 12. That is 812. The value is 0.015 amps. So it will be R to I based on the Ohm's law. So 400, 0.015 will be 6 volts. That is the same result, 60 volt here and 60 volt here. Actually, there is a fundamental approach to get the voltage in every element, but in this case, this is a series connected resistor, then the voltage will be divided by resistor values. This is voltage division. So anyway, we got the V2 is 6 volt, but in the case of the VB, what's the difference of that? Only VB is defined in this way, so VB. So the relationship between definition of the voltage Z, so VB will be minus V2. So VB will be minus 6 volt. The same circuit, but the value is different. Why? This voltage value is defined in different way, especially in the viewpoint of the polarity. So when you draw the electric circuit, every element has their own voltage and current. Then, even though the voltage and current is determined by the circuit, but when you call the voltage or current, you can define the polarity as you want. So based on that, the voltage will be positive or negative, current value will be positive or negative, based on the decision to determine the polarity of voltage and current. So important thing is the power is not different. The physical voltage and current is same, but the value could be the different based on your definition of the direction. Okay. This is chapter 3.4. We'll deal about the parallel series, parallel resistor, and current division. In the series resistor, the voltage could be the divided. But in the case the resistor is connected in the parallel way, then what happens? So you can see about that. So second element such as resistor are connected in parallel when the voltage across each element is identical. It's a kind of a dual. When Vs is connected here, then there are resistor here and here and here. And because resistor is connected to the same conductor here, so that means when say this is Vs, that means the voltage difference between 2 points is Vs. Then R1 connected to this point, R2 is connected in this point, R3 is connected in this point. That means the voltage here and here is all same. So this is V1, V2, V3 is the same with Vs. So to calculate about that, we need to check the current here. So this, we say this is Is, and I draw it this way, and we define the current is in this way, I1 in this way, I2 in this way, I3. Because I1 current through here, and current I1 and Is current through in the way, then I1 and I2 and I3 go out from this point. So Is with the same is I1 plus I2 plus I3. This is a kind of a Kirchhoff. What is that? Kirchhoff current law. So in the viewpoint of the node A, Is minus I1 minus I2 minus I3 is 0. There is a Kirchhoff's law, current law. Based on here, we can write here. Then, what is a V1? V1 is, based on the Ohm's law, I1, R1, so this R1, I1. V2 is R2, I2. V3 is R3, I3. Now, based on here, V1, V2, V3 is Vs. So that means R1, I1, R2, I2, R3, I3. So here we have equation I1 is R1 Vs. This equation I2 is, and this equation I3 is R3 Vs. Now we insert that is true here. Then what is Is? Is is I1 plus I2 plus I3 is R1 L2 1 over L3 at Vs. So there is the value of that. So based on here, how to say about that? There is an important equation here. So so in the same way, we analysis the series registering the voltage division. So we can draw the only viewpoint of the here. So we can draw the same circuit here. Vs, and currently this is Is here. Now in the viewpoint of this source, we don't care about what is here. We don't care about that. But whatever it is, the Vs and Is is same. Then we can say that is same with here, the equivalent. When IS is same and VS is same. Then we can make equivalent register here. This is REQ. Based on the Ohm's law, in this case, we get a VS REQ IS. That means IS is 1 over IEQ VS. So, that will be down. So when the register is connected in this parallel, then equivalent register is this relationship. REQ, 1 over REQ is R3. So REQ is 1 over R2, 1 over R3 inverse. That is equivalent to register when the register is connected in parallel. So when you can define 1 over R is G, this you can define the conductivity, conductance. You can define it here. Then G1 is 1 over R1, G2 is 1 over R2, G3 is 1 over R3, and G equivalent is 1 over R EQ. And you can say G EQ is the same with G1, G2, G3. This is the way how to get the equivalent, the register, when the register is connected in parallel. So there's a very important equation here. So when the circuit, the register is connected in parallel, then the source is a current source. And what happened? You can see about that. Here, this is register R1 and R2 and current source here. And we define this is V1. We'll define here, this is V1. And we define this is V2. And we define this is VS. I don't know what is better over there. Anyway, you can do that. So VS will be same with V1 and V2. And based on KCL, at the point of the node A, IS minus I1 minus I2 will be 0. From here, you can rewrite IS will be I1 plus I2. And based on the Ohm's law, V1 will be R1 I1. V2 will be R2 I2. So I1 will be 1 over R1 V1 and I2 will be 1 over R2 V2. That is the same value because I1, I2, and V1, V2, and V is the same with VS. So there will be 1 over R1 VS, that will be 1 over R2 is a VS. So we insert that here, then IS will be 1 over R2 VS. So we can make a equivalent register. So what is our equivalent register? Is 1 over R1 1 over R2 inverse. There is a way how to get the parallel register in case of, the identical, equivalent register in the case of register is connected in parallel. And the parallel register is a kind of the current divider. The series register in the previous chapter, in the series register, it's kind of the voltage divider. But in the parallel register is the current divider. Because the KCL, when current is connected in this way here, the G is inverse of the register. Then based on the KCL, the input current IS should be followed through these branches here. But based on the KCL, IS, that is going into the node, then other current, the sum of other current should be same with IS. That means the IS flow into this direction should be go out based on this branch. So this current is divided by this IS. So we call the parallel resistor is kind of a current divider. So we can make an example of that. Based on here, this is one big node. Based on KCL, IS minus I1 minus I2 minus I3 minus IN is 0. So IS is same with I1 plus I2 plus I3 plus IN. So source current is divided through these other register branches. Then you call there is a current divider here. And you should know how much current go out for each the register branch. I will give you a simple example about that. For example, this is IS. This is R1. This is R2. We will calculate how much current is divided. So we define the voltage here. This is a V1. This is a VS. It's a V2. But VS and V1, V2 same. So there are no meaning about define the V1, V2 separately. But anyway, we can do that. And this is I1. This is I2. We choose the passive conversion here. So based on KCL, the IS is same with I1 plus I2. And I don't know how much is it, but anyway, based on the Ohm's law, V1 will be, VS will be R1 I1, and V2 will be VS, will be R2 I2. And here, we can get it here. So I1 is, how much is I1? I1 is VS. I2 is alt VS. So we're adding down here. So IS will be, how much is it? R1 plus R2 VS. And what is I1? And I1 is R1 VS. I2 is R2 VS. then how much? The current divided through the I1 branch 1 and branch 2. So I1 is R1 and Vs. Here Vs is adding here. So that is a relation Is and I1. And so Is is divide I1 based on this relation. So if you are here, you can make more simply. Then R1 L2 R1 plus L2 R1 Is. That is R1 L2 L2 Is. So to summarize here, I1 will be R1 plus L2. L2, this is not R1, this is R2, is Is. Is R1 plus L2 R1 Is. This is kind of this current will be divided in this way through that direction and that direction. So this is kind of a little complicated. So we define the G conductance is 1 over R, an inverse resistor. So that is a conductivity of 1, conductivity of the 2, that is conductivity of 1. So I say I1 can written conductivity 1, conductivity 2, conductivity 1, Is in this way. There's a more general form to describe the current division here. Because you can see this is a current of 1, but the resistor is 2. This is a current of the 2, but this is a resistor of 1. So this is not complicated. This is not easy. So we define another new variable. This is conductance. Conductance is 1 of resistor. I mean the inverse of resistor. Then current can be written in this way simply. This is example of 3.4 and 1. The first circuit, the problem is the current in each branch is I1 and I2 and I3, and you need to make equivalent the circuit, and you need to find the voltage V here. That means V is the same with, actually this is parallel, that is a V. So at first, this is, R is defined and determined is R1 is 1 over 2, R2 is 1 over 4, and 3 is 1 over 8. Based on here, we can catch a point. What is the G1? The conductivity of R1 is 1 over R is 2. G2 will be 4. G3 will be 8. Based on here, we can say I1 will be G1, G2, G3, G1, Is, and I2 will be G1, G2, G3, G2, Is. I3 will be G1, G2, G3, G3, Is. There will be 2 over 14 and I guess it's 28. It's 4 amps. Then there is 4 over 14, and 28 will be 8 amps. There will be 8 over 14, and 28 is 16 amps. So we can get the R1 and R2 and R3 respectively here. And G EQ will be same with G1 plus G2 plus G3. So G EQ is G1 plus G2 plus G3. So that will be 2 plus 4 plus 8 will be 14. So REQ is inverse of GEQ based on the definition of conductance. So that will be 1 over 14. Then finally, we can get a V is IREQ. So 28, 1 over 14 is 2 volts. This is another example, is 3.4 and 2. Here we need to find the voltage measured here. So that means we want to know how much voltage applied at the parallel resistor branch, and to show the power observed by the two resistors and equal to the supply by the source. So at first we need to figure out what is the voltage here. So to do that, we define that is voltage here. So we define voltage is Vm. Actually, it depending on you. If you want, then you can define for Vm is in this way. So that is your preference. You can choose so that voltage polarity as you want. But I'd like to, in this case, I will choose in this way. Then to get here, I will rewrite this circuit with one equivalent resistor here. Then this is 0.25 amps, and this is the Vm. Then REQ, then REQ is R1 parallel and R2. The definition of that, there was 1 of R1, 1 of R2, and inverse. So that will be R1 plus R2, R1, R2. So, because this is 40, 10, 40 plus 10, 450 is 8 ohm. So this is 8 ohm. Then I will define the current here. This is I. Then the Vm is Ri. This is Ohm's law. The R will be 8 and I. But as you see, the current, I make this direction here. This is I decided the direction of the icon here. But based on the current source, current flowing through this way, so we can check I is minus 0.25. So that will be 8 minus 0.25. So How much is it? This is minus 2 volts. Why? Oh, why this is the minus? Because I decide the direction of polarity of VM is this is plus, this is minus. If we decide that the definition of VM is in this way, then there is plus 2 volt. And I decide polarity of VM is in this way, so the value is minus 2 volt here. Okay. Then we need to get the power observed by resistor and supplied by current source here. So anyway, this is VM is calculate is minus 2 volt here. Then we need to check the current here. I will define this is I1 and this is I2. So I1 is VR1, this is Ohm's law, and I2 will be VM R2. So VM was minus 2, then R is 40. That will be, how much is it? How much is it? 0.05 ampere. But polarity is minus. Excuse me. Polarity will be minus. And in this case, minus to 10 will be minus 0.2 ampere. So we choose the passive combination here and here. Passive combination in here and here, because I choose the voltage polarity plus here and current go into the plus, so this is passive combination. So next we check the power as R1 is VI and V is minus 2 volts and I was minus 0.05, that is 0.1 watt. Because we choose the passive combination, that means the positive value of power means this element absorbs the power, 0.1 watt. And PR2 is VI, V is minus 2, and I is minus 0.2. That was 0.4 watt. In the same reason, because we choose passive convention, the positive power value means the element absorbs the power. And third thing is PS. And this is also VM, and concentration is also passive rotation. So what is VM? VI is minus 2 and current is 0.25, means minus 0.5 watt. As you can see, because we choose VM is here and current is goes to the positive, so we also choose passive combination here. So in this case, negative power means this power, magnitude of the power is supplied by this element. So 0.5 watt is supplied by this source and 0.5 watt is absorbed by the two resistors. This is chapter 5, 3.5, and in this case, until now we discussed about the resistor is connected in series and your resistor is connected in parallel. In this case, we are talking about the series voltage source in the parallel current source. Why voltage is series and current is parallel? Because the parallel voltage is not happen, because it's short circuit problems. So generally, the voltage source is connected in series way, and current source is connected in parallel. Why? I will give you an example. This is a 5 volt. This is 3 volt. Then connect here. Then what is the node voltage here? In V. In viewpoint over here, this is 5 volt. Viewpoint over here, this is 3 volt. And V is 3 or 5. This is not common. So this is not allowed in the electric circuit. So parallel connected voltage source does not exist. If we connect the voltage source in parallel, then that value should be exactly the same. That is possible. But this is a very special case. So what happened here? 5 and 3 volts. The huge current go into here. So this is bound. So you should not connect the battery 10 volt, 5 volt, and connect here. This is burn out. The same way, this is current source here. This is 3 ampere. And this is current source. This is a 5 ampere. So based on this current source, the current flowing this line is 5 ampere, 3 ampere. But in the viewpoint of this current, that should be 5 ampere. What value of current here? The 3 or 5? This is not common. So this is not allowed in the current source. So in the case of current source, you can connect here in series. Not series, it's parallel. 3 amps, 5 amps. Then the current will be, sum of that is 8 amps. So current source generally connected in parallel way, and voltage source connected in series way. So the same junction can be connected VA, VB, or this is opposite junctions. And current is not allowed here. Not allowed. So in this case, let me check again. This is a plus. This is another plus. So we can say this VA is a plus, and this is VB. Then what is the value of the voltage? Here VB and VB, so that value V is VA plus VB. But if this is another case, this is a VA, but VB is connected in this way. VB, the direction is opposite of that. Then what is the value of V? So we need to check it. Because from here to here, because VB is defined the base minus and plus, so this here, the voltage here is minus VB. And from here to here, this is positive VA. So from here to here, the V is minus VB plus VA. So we can check this is voltage here. In the case of the series connection. This is a parallel case. The parallel case, current is allowed here. So current is connecting this IA and this IB. So this current is sum over here. So we can make one current source IA plus IB. In the case of this direction is IA here, the IB is going down. Then we need to see how much current flow here. IA go up and IB is go down. So the current is IA minus IB. So in the current source, the one equivalent source can be written in this here. The voltage source is not allowed in this case. So this is example of that. So it's not difficult. It's very simple. You don't need to be worried about that. The first problem is find I1 and V2. So there are four sources. There's one voltage source, one current source, one current source. So you see it looks like complicated, but based on the series voltage connection, and this is parallel current source connection. So based on here, so we can rewrite the circuit more simple. Yeah, I will write more simply. We'll draw the circuit again. Here 32 volt and 14, and here resistor and current source here, Z and 40, and this is V2, and 20, this is I1, this is 2 amps, and 3.5 amps. So in the viewpoint of the voltage value and current value here, this is not important here. So we need to simplify this second here. So first, what is that? Here we can see here, this 32 volts up and 14 is minus. So we can, this is one source. 32 minus 14 is 18 volt here. This is simplified one voltage source, and you can rewrite other register here, 4020, and this is V2, and this is I1. And we can also simplify here. We don't care about what kind of voltage current flow here. The concern is the current of that. So we can simplify. That is one current source. Here, how much is it? 2 plus 3.5 is 5.5 amps here. So based on this circuit, you can start this design. You can solve the problem here. So because this R2, this V2 is connected in this here. So how much is it? V2 is 18 volts. And I1 is current flow here, because based on the source, the current flowing here is determined by source 5.5 amps. So I1 will be 5.5 amps here. It's a very simple problem. Okay, this is chapter 3.6. It's a circuit analysis. This is a kind of the summary of the circuit analysis based on the KCL and KVL. So in this chapter, we'll discuss about the fundamental law to analyze the electric circuit. It's KCL and KVL. And we'll discuss about the resistor circuit, especially resistor is connected in series and were resistor is connected in parallel, then how to solve the electric circuit and how to analyze electric circuit in the case of a series connected resistor and parallel connected the resistor. Next, we discuss about the kind of the connection of the series connected voltage source and parallel connected current source. Based on those topics, in chapter 3.6, some more complicated electric circuit will be presented. Then we have some exercise to analysis the electric circuit. I told you several times, what is the meaning of analysis electric circuit? That means every element, the voltage and current, can be obtained. That means we can analyze the electric circuit. And to do that, we have to, I will give you some tips to how to solve the complicated circuit, like this one. The first thing is use equivalent resistor. That is the first tip I will give you present to analysis the electric circuit. From chapter 4 and 5 and 6, we will discuss about another the tips to analysis node equation and mesh equations and Thevenin equivalent circuit, and that is a kind of a techniques to analysis electric circuit. The well-defined, well-designed way to analysis electric circuit. The first thing is here we discuss is equivalent resistor. So as you see, this circuit is looks complicated. So to get, what is the meaning of the analysis of this circuit? That means we know the current here, current here, current here, current here, current here, current here, and we know all of the voltage here, here, and here. That means we should know, and then we know the electric circuit. That is the analysis of electric circuit. But my concern is not only, my concern is not this specific voltage here, but my concern is voltage here, only here. Then we don't need to analyze all current and voltage R1, R2, R3. In that case, we can focus on how to get that values here. So to do that, we can eliminate the complexity based on the equivalent resistor. Because we don't care about this R1 and R2 and R3. We don't need to know about what is V1 and V2 and V3. So then we can make that is a one equivalent resistor RS. And actually to get a Vout, we don't need to, because Vout is not only the voltage R6. VO is the voltage of R4 and R5. So we can, in this case, the Rout and VO is a voltage in these terminals. So then this resistor can be omitted. We make a equivalent resistor here. Then VO is the same. So then we can get simply the VO here. Because what is RS? RS is a switch connection of R1 plus R2 plus R3. And what's RP? P means parallel. Means, what is that? One of R1, R4, and one of R5, and one of R6 inverse. Then, what is VO? VO is voltage division of RS and RP. VO is RS plus RP, RV, and VS. So, just simple calculation, we can get a VO. So using equivalent resistor is very fundamental and basic technique to simplify electric circuit and gather some some voltage and current very easily. So we call this as a equivalent resistor here. So actually, if you want to know that is a V or various current here, and in here there are very complicated structure of the resistor. Then in this case, we don't need to know about what is the value over here, voltage and current and voltage. I don't care about that. My concern is only here, V and current. Then we need to simplify this circuit, like just one resistor. That is a kind of equivalent resistor. Because if we should know about what's the value of it, this is V, or what is the current over here, then we cannot simplify this resistor branch like one resistor. Because of that, we cannot get information about the current and voltage here. So in this case, we need to know about this branch's current and voltage here respectively. But if we want to know only the terminal voltage here and current, then we need to simplify that as a one equivalent resistor. So I will give you some example how to make this simple equivalent resistor. So first, I want to simplify here because it's simply connected in series. So we draw that is here there is 15, 25 and 20. That is a 52 and 28 is 80. Then that resistor is parallel. So you can redraw. Resistor here is 15, this is 25, and this is 20 and 80 in parallel. That is parallel. So what is that? 1 over 20, 1 over 80 inverse. That is 85 inverse is 16. So this is 16. Then this is series current here. So we can make one resistor here. How much is it? This is 15, 16, 25 is 56 ohm. That is one equivalent resistor to represent. This is a resistor branch here. This equivalent resistor. So using the parallel and series resistor techniques, so you can simplify the resistor step by step.